Hello and welcome to lecture 56 of the course Computational Complexity. In the previous lectures, we discussed communication complexity. Right? This was a model where there are two parties, Alice and Bob, and they together want to compute a certain function. And what we measure is the amount of communication that happens between Alice and Bob. And both of them are considered to be computationally powerful, but what we focus on is the extent of communication that happens between Alice and Bob during the computation of the function, right? So we described the model, and we saw what is a protocol, we saw what is a definition of communication complexity, right? And we saw this example of a protocol tree, right? So where Alice speaks, and then it's a binary tree where they exchange, like based on the Alice says something, maybe then Bob says something, then Alice says something back, right? So there's a tree, and at the end the leaves indicate that the function value is 0 or 1 or 0, right? So something like that. So at each leaf the function value is a certain number. And we also saw the definition of combinatorial rectangles. So combinatorial rectangles are certain rectangles in the, so they need not be contiguous rectangles, but they are rectangles in the matrix that indicates that is described with the function that they are computing. And we further said that each node of this protocol tree corresponds to a combinatorial rectangle, and that each leaf corresponds to an F monochromatic combinatorial rectangle, right? So let's consider this leaf that I am circling with blue. So this leaf will correspond to a one monochromatic rectangle. So this will correspond to a set of inputs, right, in the matrix that will be a one monochromatic rectangle. So it need not be a contiguous rectangle, it could be something like this. It could be 4 pieces or something like that, right? So all of these will be all of the entries here will be ones, right? So this is what we said, and because of that, if any partition of this matrix, right? Let's say we try to divide this matrix into monochromatic rectangles. If we consider a partition, and whatever way we try to divide this matrix into monochromatic rectangles requires at least t rectangles. The smallest number of rectangles that you can split into, smallest number of monochromatic rectangles that we can split the matrix into is t. Then we need to have at least t leaves in this tree, right? And so the deterministic communication complexity is at least log t, right? So which is what this highlighted result here. This is what we saw in the last lecture. And we also saw the one lower bound for the function disjointness, also for equality. So now we will, in this lecture, we will see we'll see 2 or 3 techniques that build on this combinatorial rectangles. We will see 2 or 3 techniques to get lower bounds for communication complexity. Okay, so these are since we are not, this is not a course on communication complexity, these are just introductions to some of the techniques and some very basic simple steps. If you are interested, there is a book on communication complexity by Kushilevitz and Nisan. You can check that out. Okay. Anyway, for disjointness, we saw that consider x complement and y complement. We saw that these are disjoint, but at least one of the pairs xy complement or x complement y must not be disjoint. So they cannot be in the same rectangle, is what we said, right? Same monochromatic rectangle, right? So now let us try to generalize this idea. So this type of argument is called Fooling set argument. And this was implicit in Yao's paper that introduced communication complexity, but made explicit later by Lipton and Sedgwick. Okay, so the idea is to show a large set of inputs, large set of input pairs, such that none of these pairs can be in the same rectangle. So if you show 100 input pairs, none of which can be in the same rectangle, then all of these has to be in separate rectangles. So there has to be 100 rectangles, and that gives you a bound on the number of leaves, and therefore a bound on the height of the tree, right, which is what we are looking for. So what is a Fooling set? A Fooling set for a function f is a set of input pairs, right? So S is a subset of x cross y. If there is some z for which, for all the members of the Fooling set, for all the members of xy of the Fooling set, so S is the Fooling set, f of xy is z, and so think of z as, let's say, 0 for simplicity. So one may say that for all xy in the set, f of xy is 0, and if you take two members of the set, x1 y1 and x2 y2, now consider the cross points. So we know f of x1 y1 is z, right? So we know f of x1 y1 is z, we know f of x2 y2 is z. What the claim is that at least one of these two, right, either f of x1 y2 or f of x2 y1, one of these should not be z, right? One of these opposite diagonal entries should not be z. So because of which they cannot be in the same rectangle, right? So z could be 0 or 1, right? So this is what we mean by Fooling set. All the members of the set should have the same function value, but if you take any two members of the set, x1 y1 and x2 y2, then either f of x1 y1 x1 y2 should not be z, or f of x2 y1 should not be z. Okay, so maybe some simple examples are in order. Equality. So consider the set of all numbers f of xx. Consider a set of all numbers x comma x, and these are, so we know that f of xx, or where f is equality here, this is 1, right, because these are equal. But consider when let's say x1 and x2, where x1 is not equal to x2, right? We know that f of x1 comma x1 and f of x2 comma x2 is equal to 1, where f is equality, but f of x1 comma x2 is equal to 0, it's not equal to 1. So any x1 and x2 that you take, f of x1 comma x2 is not 1. So this means this is a Fooling set, right? So this means S is a Fooling set for equality. Now, since S is a Fooling set, that means deterministic, so tree has at least any tree that computes the function, any protocol that computes the function, that protocol must have at least size of s many leaves, which is at least 2 power n leaves, because there are 2 power n values of x, so 2 power n elements are there in the set S. And this means that since it has 2 power n many leaves, d of equality, we have already seen a proof for this, is at least log of 2 power n, which is equal to n, right? So this is deterministic complexity of equality. And if you recall, in the last lecture we made the similar argument for disjointness. We said that you consider S, that is a set x complement, then the cross elements may not be disjoint. So there should be at least s many leaves of the tree. So log s, the lower bound on the communication complexity is at least log s, which was again n. So same argument we are making here, just that the fooling set is different. Okay. Now we will see another example. This is a similar example, greater than. So in this case, the set is, the fooling set is the same set actually. So consider so GTN is 1 if x is greater than y when read as a binary number, right? So for all x comma x in S, GTN of x comma x is 0, because the same number x is equal to x, so it is not greater than x, right? But consider x1 and x2 where x1 is not equal to x2. Let's say without loss of generality, x1 is greater than x2, right? So without loss of generality means one of them has to be bigger than the other, right? Because they are not equal. So let's say x1 is greater. So now GTN of x1 comma x2 is equal to 1 because x1 is greater than x2. So again, this is a fooling set, because pick any two x1, x2, one of them is bigger than the other, so the greater than function will be equal to 1 for that entry. So S is a fooling set. For greater than. This implies deterministic communication complexity of greater than is at least log of the size of S, which is equal to n. Again, the size of S is 2 power n, right? You can see. And disjointness, we already saw this last lecture. This is a fooling set, as seen in last lecture. Lecture, I think 55, right? So this is 56. So this is one approach to showing lower bounds. So again, the template is we want to show that there are many leaves, so the height is big. When the height is big, the protocol, the number of bits exchanges large, right? So usually it boils down to showing lower bounds, although sometimes we also have to show upper bounds, because to show upper bounds, it's enough to show some protocol, and this is sometimes most of the time this happens to be a bit more easier. So lower bounds are more interesting. Okay, so in fooling set we try to show a big set such that none of these elements can be in the same rectangle, so the number of leaves have to be big, large, so the height has to be large. So another approach is to show a bound on the size of monochromatic rectangles. So if we say that every monochromatic rectangle is small, then we need many monochromatic rectangles to partition the entire matrix, right? So one way to show a lower bound on the number of leaves is to show a upper bound on the size of a monochromatic rectangle, right? So the statement is very simple. If every monochromatic rectangle has size at most s, right, then we need, so there are 2 power 2n elements in the matrix, right? So the matrix is 2 power n cross 2 power n, so 2 power 2n elements in the matrix. So and each monochromatic rectangle has size at most s. So any partition into monochromatic rectangles requires at least 2 power 2n divided by s many rectangles. So this is the T that we stated here, right? Any partition of x cross y into monochromatic rectangles require at least T rectangle, this T. So df is the log of this, and the log of this is the log of 2 power 2n minus log of x. So log of 2 power 2n is simply 2n, and log of s is log of s. So this is one way to get a lower bound on the communication complexity. Okay. So we'll see one example for this. In fact, it will be slightly different. So what we will show here is, we will show that the function is disjoinous. Again, we have seen a lower bound for this, but this is another approach. So we will show that the size of any one monochromatic rectangle is at most 2 power n. Okay. So this by itself is not enough, because we have to show that to get a lower bound, we have to show that the number of rectangles is large. But here we are only upper bound in the size of a one monochromatic rectangle. So if so this is not going to be enough. I'll explain at the end of this proof. But it's easy to fix. Okay. So why is the size of any one monochromatic rectangle in the disjoinous matrix at most 2 power n? Okay. So consider the rectangle, let's call it R. Okay. So this is a one monochromatic rectangle. So maybe there is some set, I don't know, S1 here, some set T1 here, right? So maybe I'll write R to the corner. So this is R, and all the entries here are 1, right? So this means S1 and T1 are disjoint. Okay. So now we have many sets, let's call Si and Tj maybe. So S1, S2 and so on, and similarly T1, T2 and so on. Okay. So suppose R is, so we want to show that R has size at most 2 power n. So let there be L columns. So I say L cross B, so but I have marked B cross L, so maybe I'll fix this. So L cross B matrix R. Okay. So this is a one monochromatic rectangle. Now consider the union of all the rows, which is T1, T2, etc. Okay. So there are L rows. So the union of all the rows, so UA, we call it UA. Maybe I'll use another color. UA is just nothing but union of I or j equal to 1 to L Tj. Okay. And UB is the union of all the columns I equal to 1 to B Si. So UA is the union of all the sets. So when I say union, I mean union of the rows, I mean this union of the sets denoted by the rows, and the union of the sets denoted by the columns. Okay. So now each one of S1, any Si is disjoint with any Tj, right? So for any, this is a one monochromatic rectangle. So any Si, right, for any I comma j, Si and Tj are disjoint, right? So it should be the case that even for the union, right, union of the union of the rows should be disjoint from the union of the columns, because any one of these is disjoint, so the union also will be disjoint. So union of A and the union of the rows and the union of columns will also be disjoint. Okay. Okay, so which is not very difficult to see. Now consider a bigger matrix, right? Consider a bigger set. Now consider all the rows that are subset of UA. Okay, so UA is the union of all the rows here. Now consider there could be other rows that are subset of UA, but not in this matrix R, not in this rectangle R. And consider all the columns that are subset of UB, even those that are not in R. So this could possibly be, so let's say this is R. What I am saying is, consider all the rows that are subsets of UA. So there could be other things that are not in R, right? So maybe I'll use red color. So maybe it's something like this. So this is all the subsets of, so but then R will certainly be contained in this, because all the rows corresponding to the rows of R are indeed subsets of UA, because UA was constructed by union, taking the union, and all the columns of R are subsets of UB. So that will so R will certainly be a subset of the, this matrix. So now consider this matrix R prime, and what we are the claim is that R prime is a superset of R, which is also not very difficult to see. What we will show, so we wanted to show that any one monochromatic rectangle is of size at most 2 power n. So we want to show R is of size at most 2 power n. In fact, what we will show is R prime is of size at most 2 power n. Right? So which means R prime is it's a superset of R. So which implies R is also of size at most 2 power n. How will we show that? So what is the number of rows of R prime? R prime has all the subsets of UA as rows. So if UA has size of UA many elements, the number of rows of R prime is 2 power the size of UA. Similarly, the number of columns of R prime are 2 power the size of UB, because the columns of R prime are all the subsets of UB. So if UB has had 20 elements, then R prime will have 2 power 20 columns. Okay. So the size of R prime is nothing but the product of the number of rows and number of columns. So 2 power UA, size of UA multiplied by 2 power size of UB, and the product of that is 2 power size of UA plus UB, right, which is what we have here. So R prime is of this, and I already mentioned that UA intersection UB is empty set. I mentioned it here, right. So we have that UA intersection UB is empty set. So what is the size of UA plus size of UB? Size of UA plus size of UB has to be at most n, because there are only n elements in the universe. So and the UA and UB are disjoint. So each element has to go into only one of them. If size of UA plus size of UB is greater than n, that means there is some common element, because there are only total n elements. If there are common elements, then they cannot be disjoint, right? So size of UA plus size of UB is at most n. So size of R prime is 2 power the size of UA plus size of UB, which is at most 2 power n. And this is what we wanted to show. Size of R prime is at most 2 power n, and hence the size of R is also at most 2 power n. So we took an arbitrary rectangle and showed that it's of size at most 2 power n. Now to get a bound on communication complexity, we need to show that the number of rectangles is at least something. So we showed that the size of one monochromatic rectangle is at most something. But that's not quite enough, because what if the number of ones itself is very small, right? If the number of ones itself is like 2 power n or something, then maybe if a constant number of R rectangles are enough to cover them. So that does not give us a bound. So we have to also show further that the disjointness matrix has a lot of ones. So the number of ones in the disjointness matrix is actually 3 power n. How do we see this? So one way to see this is that so look at the matrix. So maybe we'll write a small matrix. It's a 2 by 2 matrix, or maybe I'll just write something in general. So 0 0 0 0 0 0, right, up to 0 1 1 1 1 1 1 0 0 0 0 up to 1 1 1 1 1 1. Similarly, columns 0 0 0 0 0 0 1 1 1 1 1 0 0 0 0 and 1 1 1 1 1. Okay. So I can divide it into quadrants, this matrix. Now let us see what maybe it's simpler to let's say this is the matrix for n bit inputs. Okay, so this is n bits. So let us look at the quadrants. So let us see the entries here. So what is the entry over here, the bottom right quadrant? So the claim is that this is all zeros, because all of this have the leading bit equal to 1. So all of this, the leading bit is equal to 1 for the row input as well as the column input. So this cannot be disjoint. So the bottom right quadrant is all zeros. Now let us look at the top left quadrant. So the leading bit is zeros for both the column entries as well as the row entries. So this is actually, so what are we doing here? Let me call it the disjointness matrix of n. Okay. So what we will have here in the top left is actually the first entry is 0 for both the column and row. So what we have here is actually nothing but the disjointness matrix for n minus 1 bits. And the top right also is the disjointness matrix for n minus 1, because the leading entry is 1 for the column entries but 0 for the row entry. So there is no issue with the leading entry. The leading entry does not prevent disjointness, and the rest of the matrix is just the disjointness matrix for n minus 1. And by the same analogous argument, the bottom left is also the disjointness matrix for n minus 1 entries, because the leading entry for the column for the rows is 1 but the column is 0. So that there is no issue there, but the remaining entries correspond to disjointness of n minus 1. And so the number of ones in the disjointness matrix for n is 3 times the number of ones in the disjointness matrix for n minus 1, simply because there are 3 copies of the disjointness matrix. And if you look at the disjointness matrix for 1, so this is just disjointness matrix for 1, this is simply 0 1 0 1, this is 1, this is 1, this is 1, this is 0. Right? The only way they could be not disjoint is if both the rows and columns have 1. So disjointness of 1 has 3 entries, 3 ones, and so disjointness of 2 will have 3 times 3, 9 ones, and so on. So the disjointness of n will have 3 power n ones. So the number of ones in the disjointness matrix is actually 3 power n. Okay, so I am not writing the proof in full detail, but so as an exercise, you can work out the proof of 3 power n ones, proof of number of ones in disjointness matrix, disjointness n is equal to 3 power n, with full details. I have almost told you the details, but just you can write down the steps and convince yourself. Okay, so now we have seen that the number of ones is equal to 3 power n, and we know that each one monochromatic rectangle has at most 2 power n size. So the number of one monochromatic rectangles must be at least 3 power n divided by 2 power n, because each one monochromatic rectangle can only include 2 power n entries, at most 2 power n entries, and the total number of ones is 3 power n. So we need at least 3 power n divided by 2 power n rectangles. So the number of leaves must be at least 3 power n divided by 2 power n. So the communication complexity is at least log of that, which is what we have written here. It is log of 3 power n divided by 2 power n. So which, if you just work out, it is just n log 3 minus n, right? Because log of 3 power n minus log of 2 power n, but this is omega n, because it's like n multiplied by a constant, right? So this is simply n into log 3 minus 1. So it's omega n. So this also this is not exact bound, like it's not saying it's at least n, but it's at least some constant times n, log 3 minus 1 times n, right? So this is another approach to size, finding a lower bound for the deterministic communication complexity. And there's one more thing that I will just mention. So now we have seen what is the matrix that corresponds to a certain function, right? We call it M of a certain function, right? So we call it M of a certain function, and consider a 0 1 function. Consider a 0 1 function. Now, for that function, let the rank of the matrix be denoted by the, so rank of f, let the word rank of f, let us use this to denote the rank of the matrix of the above function, right, over reals. So you can compute rank over different fields. So consider the rank of the above matrix. So the matrix is defined by the function over real numbers, over the real field. Okay, and you can see that the deterministic communication complexity, so the important part I will highlight, is at least log rank of f. Okay, log to the base 2 as always. So you can see the deterministic communication complexity is at least log rank of f. Again, it's not very difficult to see this. It's a rather simple proof, but since we have limited time, I don't want to elaborate that. If you're interested, I can point to references. So deterministic communication complexity of the function is at least the log rank of f, and you can also show that it is at most the rank of f plus 1. Okay, and this is also another way to get lower bounds, and this led to something called the log rank conjecture. So it's a very popular, or in the area of communication complexity, this is a very famous question, open question. So the conjecture is that for any function f, right, there is a constant c such that the deterministic communication complexity is at most log rank of f to the power of this constant. Okay, so this above, the thing that we wrote above, the one that I have highlighted, it says it lies between log rank and rank. So rank is like much more than log rank, right? It's exponential in log rank. What we are saying is that the deterministic communication complexity is at most polynomial or a constant power of the log rank, not exponential. It's polynomial in the log rank is what this is saying, right? And this question has been open for at least maybe 2-3 decades now, and it's still unknown. And the best known bound is something like this, that is by Shahar-Lovett. The deterministic communication complexity is order square root f, a square root of the rank of f multiplied by the log rank of f. So this quantity is there, this the square root rank of f. This makes it still exponential in the log rank of f. Sorry. So it's still not known. And one thing that is known is that we know of a function, we know of functions where the deterministic communication complexity is n, and log rank of f is at most n power 0.631, right? So log rank is at most n power 6.631, and deterministic communication complexity is at least n. So this means that the c, if deterministic if the log rank conjecture is indeed true, the c should be at least like enough to power this so that it becomes at least 1. So the value turns out to be 1.58. So we know that if log rank conjecture is true, then c must be at least 1.58. And okay, there have been some series of works, but the best known bound is what I stated above by Lovett, which is this, and we know that c must be at least 1.58, and that is what is known. And this function is, again, it's not very difficult to work out. If you are interested, I will give you the details of this. That this function, it is log rank is at least this much. This function was discovered by Nisan and Wigderson. And so with that, I think I'll conclude this particular lecture. So we saw the we saw the Fooling set argument, and we saw the size bound, and I mentioned the rank bound, and also stated the log rank conjecture, right? And Again, there are other techniques, other variants of communication complexity, such as randomized communication complexity, non-deterministic communication complexity, etc., but which we will not have time to get into. In the next lecture, we will see an uh, application of communication complexity into the rest of complexity theory. With that, I'll stop this lecture. Thank you.